Greetings. Welcome to Instrumentation. We're going to play this a little differently than we normally do and do all these online. I'm going to put up two PDFs, one for Learning Pack 1, one for Learning Pack 2, or Book 1, Book 2. And I'm also going to put up a commentary walking through it and talking about it, highlighting the things that you really need to be aware of, and things to remember for the test. So let's get started. Instrumentation in Lab 213. This class is about process control, process instrumentation, and all of the devices and the instruments that we need to literally control some kind of process in the field. Well, for segment 1, we're going to start the Learning Pack 1. We're going to talk about overall concepts, specifically process control concepts. Then we'll get into some other things for that. Defining a process control. A process control can be manual. It's a desire to control some process. Everything in the world uses it at some point, a process control system, that is. They can be simple, or they can be complex. Let's look at a liquid level application. Here in a liquid level application, I want to control the level of this tank. I have a flow in. Well, I have a level sensor that lets me know what it is. That's going to feed the controller and control the valve to let the water out. So as I got water coming in, that'll let it out. If I'm above the level, it's going to open it wide so more will flow out. If I'm below the level, it's going to throttle it back so that not quite so much comes out, until I essentially have the same coming in as I have going out. And that's the level control system. It's the basics of a process control system. They're used everywhere, and I mean literally everywhere. The pharmaceuticals, fuel, chemicals, everything, food industry. Everything has some kind of process control and process system that they need to control. The thing to keep in mind about process control is always safety first. We always want to maintain safety. You want to do everything you have. Remember the PEE, people, environment, and equipment. Nothing does it say anything about perfecting sales. It's people, environment, and equipment. The proper motive, while sales does come into it, it only comes into it after safety, and only into the extent of we're meeting the product specs, we're minimizing waste, we're minimizing the energy use, and we're maximizing our production and minimizing environmental impact. Here's an example of a loose control. We really want it to control at this level, but it's not. It's controlling it down here, and it's it's all over the place. This is loose control. That's not profitable, and it doesn't work well. Here's one where the set point's a lot closer, and all my controls, my process variables are closer to the set point I want it to be in. This is going to be much more profitable. It's going to come out with a better product in the end. So, as part of that, we have three basic terms we need to know. One's a process variable, one's your set point, and one's your error. A process variable is a variable of a physical quantity, something I can measure, and it's what I'm controlling. Generally, it's going to be a numeric value, and we call it the PV. It has to be something that you can measure. Process variable is not love, it's not intelligence, it's not likes, although some people try to equate that with likes. But it's a physical variable like temperature, time, weight, force, things like that. Measuring the PV you measure it at a certain time, and that's what it is. You have to measure something before you can control it. One and more PVs can be measured. Looking at it from that point of view, we can measure temperature and time and control both. That's what we do when we cook. Here's that same example. Here's our level, our flow in, and the controller is controlling the flow in instead of controlling the flow out like I did before. Functions of process control is to measure the process variable, compare the process variable, and the set point. The set point is what level I want. I want what I want to control this at 7, then that becomes my set point. My process variable is 10. That's what it physically is at that time. And computing the error. Well, we'll get to what all these means in a minute. The desired set point is the desired value of the process, SP. The desire is for SP to equal the process variable. That's what we want. Error is set point minus PV. So basically what we're wanting to do is we're wanting to make error as close to 0 as possible. Error evaluation, size, direction, error depends on all of these things. So here we have an example. Here's our same water that's controlling the valve. Our set point is 10. Our current process variable is 4. So our error is, or 6 rather, our error is 4 feet. Or error is 4. So we want to control our controller to reduce that error. We want to get that down to 0, or as close to 0 as we can get it. 5 common process variables that we deal with all the time are flow, level, pressure, temperature, and chemical analysis. We won't generally get into chemical analysis much here, but that also includes pH balance. How much hardness is in the water and all that other stuff. Here's a flow example. I got hot water coming in. I got a flow sensor to heat exchanger. I want the flow rate to be 10 inches per minute. So we use a controller to do that. Same level control we've seen before. A pressure control. I have a pressure sensor that measures the pressure inside the tank. I want the nitrogen out and the nitrogen in to have a difference of 3,000 kilopascals. And temperature, the same thing here. I read the temperature here on my output, and I change my valve on the hot water going in so that it raises the temperature in my heat exchanger here. And chemical analysis is reading the pH here, and I actually pulled up pH balance. It's reading the pH sensor. There are 2 types of process variables that we need to worry about. The controlled variable, what I'm trying to control, and the manipulated variable, what's actually changed. It's often different from the control variable. Look at the liquid level. The controlled variable is my tank. My manipulated variable is the valve and the flow rate based on the valve. So I'm actually controlling the valve to maintain the flow rate. So there should actually somewhere be in here a flow sensor that actually feeds back the flow rate to the controller. Go through these, fill those out on your own. This is the second section or segment of this set. Process instruments. Devices that do 3 things with the process variable. We can measure them, we can control them, and we can manipulate them. We can either do it directly by doing it by hand or with a controller or however, or we can do it indirectly. And we're not limited to those. Measurement instruments, measure flow, temp, things like that. We use sensors. It determines the size and the existence of a process variable. You can tell us if you can get a temperature and there's 0 temperature, there's nothing there to measure. If the flow is 0, that means there's no liquid coming out, as long as the sensor is actually correct. The control instruments can be like computers, PLCs, electronic controllers. They're the ones that actually work to control the SP and the PV, make them the same. Generally we will be using specific controllers within our labs, but you can use a PLC or computers to do the same thing. And manipulation instruments is a fancy word for saying what we call final control elements. Our control valves, our pumps, things like that. We control those to change things going in and out. All right. Control loops is a system of process instruments. That's basically one big thing, the whole thing. Here's our tank. This constitutes our control loop. Input sensor and my output going through a controller. The most basic type of control is open loop process control. It has a control instrument. It has a manipulation instrument. But it doesn't have any means of sensing the output, and it doesn't correct the error. Think of this more along the lines of you got a controller manipulating the valve, but someone has to manipulate the controller. Man says, well, I got to get down here. I got to spread it out so it goes up, and it increases the valve size so that more flow comes out. I think of it more along the lines of a guy standing over a tank with a hose. Like you're filling up your pool. Standing over the pool with a hose pipe. Getting full. I need to shut it off some. That's open loop process control. There is no feedback. That's the key part of open loop. No feedback from the process. It's simple. It's low cost. You can't maintain the set point if conditions change, and it's not good for tight control. That's the disadvantages and the advantages. You need to know this one. This is one that you'll need to know. Closed loop is just like open loop, but you have a feedback sensor that gives you your measurement. And it feeds that back into the controller. So here's where error comes into play. And it's an error that gets measured so it can go back into the controller for it to manipulate for change. Here, I'm controlling the valve, sensor, and the output. My feedback is that coming into the controller so that the set point, it can be compared against the set point, and I can change the output. If my error is which is set point minus the process variable, which is the feedback, if it's getting close to that set point, if it's getting to zero, then it's going to shut the valve off. But then it's just going to keep going there. So it needs to maintain this valve so that the flow going out is the same as the flow coming in. Closed loop, many advantages. Has a constant output under pressure changes, good response time, and time control. Disadvantages is it's expensive. It can be more complex. One thing we need to talk about. That was the first book. Actually, the first segment of the first book. Segment 2 is safety. We should have been talking about this beforehand, but for some reason they wait till the second book for this. Safety is paramount. It should be the highest thing you should be thinking of all the time. Processes all involve safety hazards. There's something that can break, something that hurt people, hurt you, and hurt equipment. Use common sense. I know it's not always common nowadays, but use common sense. A little bit of common sense goes a long way. Machinery doesn't care what you put in it. If you're using a stamping machine, it doesn't care that your hand's there or that a piece of metal's there to stamp. It doesn't care. It's going to stamp regardless. There's no brain there. It's unforgiving. Electricity is unforgiving. If you have less resistance in your system than whatever it's going to, and you put your hands across it, it's going to go through you instead of that. And that could lead to disastrous results. Most accidents are preventable. I'm going to say almost all, 98% of accidents are preventable. Somebody was doing something they shouldn't have been doing. They're driving a forklift too fast or whatever. But they all should be preventable. When you're on the job, use your hard hat, safety glasses, roll your sleeves up, and then heavy-duty boots. Now, a lot of times this sleeves thing, I take an issue with. If you're in a steel mill, you want your sleeves. You won't wear sleeves all the way. You want your arms covered so that you don't get burns from slag and things from welding. What they mean by the rolled sleeves is they mean no loose clothing. You don't need to have loose clothing floating around while you're working. That means no loose jacket that could connect to something that can break something. 6 rules. Always wear your safety glasses. It says loose fitting clothes, but it's not loose to the point where it's flowing. No loose fitting clothes. No jewelry. Hair, no long hair. If you have long hair, it should be tucked up. Make sure you have metatarsal safety shoes and that your sleeves are appropriate for the job being done. Now, Rules for process safety: be aware of where you're working, what you're doing. When you're working on the process, lock out all power sources. Make sure you understand your company's lockout, tagout procedures. Always assume it's loaded. Assume the gun is always loaded. Don't rely on your safety devices because they can break. And that goes with the phrase, assume the gun's loaded. Make sure your equipment is grounded. That's both the piece you're working on and the one you're plugging in. Keep your test equipment organized. Don't ground yourself, and don't provide an electrical path for the current to flow. Watch what you're doing. Always have a buddy. Don't work by yourself, and stay focused. Don't try and do it when you're half asleep. And do not trust anyone's word that, oh yeah, that machine's safe, I took care of it. Look for yourself. Make sure that safety switch is turned off. Make sure it's unplugged. Make sure everything is off that thing that could cause any motion. Make sure it is in a stable state before you do anything. And also make sure you understand what the system is supposed to do and what it's capable of doing. Don't override safety devices. We had a problem with that, and I imagine they still do at Heil. We used a proximity switch, which you'll find out about later, to tell whether or not a tailgate was up or down on the back of a garbage truck. Excuse me. And if the tailgate was up, we'd have an alarm going off in the cab. It was an annoying alarm. It was meant to be annoying. It was a loud dinging sound. Well, come to find out, the guys working on the floor didn't want to hear that all the time, so they taped a washer to that proximity switch. Well, it just defeated that safety device. That's there to let you know the tailgate's open, and don't walk around that tailgate unless you are careful and know where it is and what it's doing. When they did that, they overrode it just so to get that alarm from going off. They violated the safety system. They overrode it. And also, watch your heavy lifting. Only lift what you can lift. Lockout, tagout safety. Live equipment is dangerous. You're required to have training by OSHA on lockout, tagout procedures, and most companies go through a yearly refresher on those. You are responsible for your safety and your life. Your buddy is only going to go so far. But at the same time, you can be hurt because your buddy didn't do something he was supposed to do. Lockout and tagout are two different things. We call it lockout, tagout, but lockout and tagout are two different things. Lockout is where you have a clamp or something that you put on the power switch or a switch to keep it from moving. The tag portion is an indicator of who tagged it out, who put the tag on there. It should be permanently attached to the lock and should never be removed unless it's being replaced. When you perform a lockout, tagout, shut off all the power sources, close all the valves so that nothing will be flowing, and block any mechanical movements. In our tailgate instance that I talked about, we had a device that was a stand that would stand there and hold up the tailgate, or would sit under the tailgate to where if the tailgate failed, it would grab it and prevent it from closing all the way and cutting someone in half. Lock everything out that's applicable. Use locks and appropriate tags. Don't just put a paper clip in it saying, oh, it's on, because somebody can remove that. The reason we use locks is so that you have the only key to that lock. For that to happen, you've got to be the one that unlocks it. This is successful, locked out and tagged out. We have these on our test stations, and we'll use them every day. You have to remove all the energy from the systems. If you're dealing with capacitors, like on TV sets, you need to put a bleed resistor across it, because that's the purpose of the capacitor, is to store charge. And that means even with the power off, it's got power on it. And there's enough in a capacitor in an old TV set that can kill you. Same thing for mechanicals, springs, fluid, gas trapped in lines. Always vent and drain lines. Steam, the whole 9 yards. Anything that can be stepped, it needs to be in an inert state with nothing flowing, nothing moving. All right. Book 3, manual control. It can be closed or open loop. In a manual system, the human is a controller. We have a control here, but it's Fred here. The operator sets the control variable to the set point. The operator checks to see if the controlling variable is a set point. There's very little control. Accuracy is not critical. Process changes little, and it will be used for fix. In other words, I'm going to set this, and it's going to stay that way forever. That's one way of doing it. Here's one way, because we've got a valve here, manual valve, so I've got a twist to change that level. And it just sets it so that the flow out's the same. They can be controlled closed loop because the operator can see the level, and that is your feedback system. It doesn't have to be an electric feedback system, but it's a feedback system nonetheless. The operator does manual operating visually and makes adjustments as he sees fit. Now, this is somebody that you're going to pay a salary to. You're going to pay company's going to pay insurance. Going to do all this stuff for him. So that's why manual processing is not as efficient as others. Manual closed loop, we don't use it much today. It's not very cost effective. It's not good when precise control is needed. If you got to control it to a type error, manual control is not it. Here's another review. And as part of our manual, we'll look at sight gauges. Sight gauge is just that. It's a gauge on the side of a tank or something like that. It'll let you know how much fluid is in there. Like a liquid level in a boiler. We use them in hydraulic tanks. It may be a scale, it can be external. There's lots of ways for it to happen. But it's going to give you some indication of how full it is. There's a float type. This goes up and down. This changes on this side. There's a couple more. There's more of that, and that's it for this lesson. We will have our first lab on, I believe it's the 27th, whatever's in the syllabus. So join us in the lab that day. Thank you much, and have a good day. Bye now.